because she said, because usually we get a note card, but we're not allowed to have a note card. Our cheat sheet is the periodic table of elements, so we get the whole paper.
Gotta love that.
And so that's our cheat sheet, and I really need to have that. Exactly.
Oh, goodness. All right. So this subject, actually, I bring in a few animations and a few video clips to kind of reinforce this subject. One of my favorite podcasts on astronomy, always, their slogan is, not only do we tell you what we know, but we tell you how we know what we know. And to me, that's kind of what your author's done in this textbook. For instance, we talked about the distances to galaxies. Not only do we know how far away galaxies are, but like, how do we know how far away galaxies are? So with this topic of, especially we're going to talk about dark matter and then kind of finish up a little bit with dark energy, it's like you can't see it. So how do you know it's there, sort of thing, So that's kind of, this topic is really into how do we know it's there, sort of thing. Okay. So what dark matter and dark energy both have in common is the term dark just means we can't see it. Now it's funny because can you really see energy? You can see energy because it does things. Do you know there's energy when you plug something into the wall? No, but if you're trying to run something, you can see it running something, okay? Matter, that's a different subject. That's a different topic. We can see the matter, okay? Okay, but dark matter, we know it's there because it's influencing objects, okay, but we can't see it. And actually, we're going to see that some dark matter is just because it's not lit up, okay? That's actually called, those are called machos, massive compact halo objects. They're not lit up. The other thing about dark matter, though, we think is they actually are another type of little subatomic particle. So if you're familiar with the big roar over the Higgs boson particle, okay, that actually kind of went at, we're familiar with little atoms made up of protons and neutrons and electrons. Well, actually, you can break those down into smaller particles. And so maybe dark matter is kind of one of those smaller particles. So it's possible to kind of look at matter and energy kind of a little bit interchangeably. Okay, Einstein said E is equal to mc squared. So in that sense, they actually can be converted back and forth between each other. Energy and matter, that's the mass, the M term. But if we look at the universe as a whole, the normal stuff is kind of small. The dark stuff is a lot. Ooh. Okay, I'm going to try to convince you how we know about this dark stuff, whether it's dark matter or dark energy. Okay. Normal matter, by the way, I looked it up because I wasn't sure of this, but it's called baryonic matter. And I know I have heard this like in Star Trek. So baryonic matter would be your normal atoms with nucleuses that have protons and neutrons and electrons spinning around them. So we have a lot of dark stuff, whether that's dark matter or dark energy in our universe. Okay. So this, I have a few little applets to kind of build up to how do we know that dark matter is there. Okay. And there's a few ways that we can understand that the matter of something has an influence on objects. So for instance, as planets orbit the stars, in this case, this is kind of our solar system, we know that that sun in the middle of our solar system is influencing how the planets go around, okay? The planets, if the sun were not there, the planets would not do this, okay? And actually, and it's I want to say it's a Newton thing, came up with this relationship, okay, that the mass that has something orbit around it, that's this right here, okay, the thing that's orbiting that particular mass, okay, will have this v, that's the velocity, if it's at this r, that's the radius, and the g is that constant. Okay, so in this case then, it makes a difference as to the mass that something's orbiting. Now, one of the things we talked about is that when our solar system was made, so that's our sun, of course that's Mercury, Venus, the blue one, the dark blue one's the Earth, and the red one is Mars. Mars always has to be kind of red, doesn't it? Okay. When our solar system was being formed, the sun got most of the mass, and actually that's what this is going to show you. So if I click here, and I draw outward. Okay, so now I have the sun and Mercury. Okay, and oops, wow, that really zoomed up. And so here is the mass down here. That's different. Now, maybe it'll reset. Let me go back. That is so bizarre. I guess we'll open that up again. Okay. Now let's try it. Okay, so first let me take the sun and I'll go out. Okay, now that little yellow dot right there is the mass that's in that circle. Okay. So there's no planets in that circle. Let me go ahead and reset, and let me catch the closest planet. I don't have to catch it, but actually the closest planet, of course, is Mercury. Let's see if it likes this better. Wrong mouse. Reset. Really? Okay. So let me catch, now let's compare that second dot right there. Actually, looks like there's another dot. But these dots are actually kind of just looking at the same mass. Let me go ahead and go clear out to Mars, and we'll see how much mass is inside the orbit of Mars and compare it to the other ones. That'll be our last one. Come on. All right. Not much change. The point here is basically all of the mass that is in our solar system is mostly kind of just in the sun. The planets are just kind of like little tidbits. And that has consequences. Let me go ahead and put the equation back up here. That has consequences. Basically, this is constant. This is the same. This is the mass of the sun. And as the planets orbit the sun, we know that as r gets bigger, r is the radius between the sun and the planet as it orbits the planet, or as the planet orbits the sun. Okay, as that gets bigger, we know that the velocity goes down. Okay? As r gets bigger, the velocity goes down. Mars is going slower than Mercury. Okay. So the cool thing about this is we can actually, Newton could, okay, use this to get to the mass of the sun. All right. Doesn't have anything to do with dark matter yet. Just has to do with stuff being influenced, planets, being influenced by the mass of a star or the sun as they orbit the sun. All right. So this one's a little bit different. Let's see if this one behaves. So for this one, the thing that's being plotted is a little bit different, like I said. If I click on the, right there, I clicked, of course, on the orbit of Mercury. That's how fast it's going. And notice then if I click on the orbit of Venus, it's going slower. If I click on the orbit of Earth, slower still. And the orbit of Mars, slower still. Okay, so we can use this as the v squared term in the equation we saw a minute ago, and the radius to get to the mass of the sun. Because that's what's influencing the dance of those planets. So a little bit different. Have you ever been on, or put your kid on, because they aren't safe, Put your kid on one of those like merry-go-rounds that are about this big, and they look like a flying saucer. Okay, that's what this reminds me of. And the thing is that's what we call like a rigid body. So there's your flying saucer merry-go-round. Okay, and the thing about it is if you were to sit, it has a constant spinning, okay? But can you see where if you're out here at the edges, when it completes one rotation, you have gone this far, okay? And if you're near the thing, when it completes one rotation, you've gone this far, okay? So as far as speed, okay, if you're close to the center, okay, your speed is like that, okay? And if you're far out to the edge, okay, just by nature of being at the edge, your speed is that. That's a rigid body, okay? Has nothing to do with gravity in this case, but just kind of how a rotational curve. Let's go ahead and kick it up a notch. Ah! Okay. So we know something about an object by watching stuff spin or rotate. That one has nothing to do with gravity. This one does have to do with gravity again. So what you're looking at, or what I'm going to show you, is, bless you, another little kind of scatter plot. And this is actually the Milky Way galaxy. It's not a photo, is it? Okay. And it's looking at the Milky Way galaxy face on. Okay. So one of the things that we know, and to me it's kind of weird to think that, you know, we're here in the Milky Way galaxy and yet we understand how stars are orbiting that supermassive black hole in our galaxy, okay? But we do, or someone does, okay? So as I click here, for instance, okay, that is how fast it's orbiting the center. And I'm just going to kind of go out, I think. Okay, so I'm going out. Now, if this was like, you figure the supermassive black hole's pretty massive. Supermassive black hole's got a lot of weight. And if it was like our solar system, all the weight would be concentrated in the center of our galaxy. And if it was like our solar system, then kind of like when we got to Mars and let alone Jupiter and Saturn, things would slow down. But they don't. In fact, we can look at objects clear out here, okay, as to how fast they're orbiting. They're going around, okay? So the thing here is the mass is not just central, is not just in the middle of our Milky Way galaxy. In fact, like the next slide says, the mass is just crazy, how do I say, actually the next slide kind of shows you, go back. We can use those velocities to see where the mass is. Okay, so we can use velocities to see where the mass is in our solar system, the mass is in the sun. Where is the mass in the Milky Way galaxy? Well, we'll start from the beginning, and the mass kind of accumulates. Starting in the beginning, or starting, oh, I guess I have to do it this way. Starting, that's how much mass is in that circle. Reset. I'm going to make the circle a little bit bigger and see where our dot goes. That's how much mass is in that circle. Okay, so that's kind of almost to the edge of our galaxy. Let's go out to the edge of our galaxy. That's how much mass is in that circle. So the mass isn't petering out. You know, it's weird because we said the Milky Way galaxy, remember, it's thicker at the nuclear bulge and gets thinner about 1,000 light years out at the edge. So you're like, dude, there's not many stars that we can see out there at the edge. But the mass is constantly just crazy big out there. In fact, I'll go beyond where there are stars. Seems like a Star Trek slogan. So this actually is beyond where there are stars. And we keep adding mass. We keep adding mass. Mass we cannot see. Mass that is dark. The stuff that you can't see, okay, That's dark matter. And I think I like your next slide because it actually shows you, I guess it's coming up. It's on the next one. Okay, so we said that, and I don't know if you commit it to memory, but you guys maybe told me on your test, that last page, that the Milky Way galaxy is about 100,000 light years, okay? So you figure 50,000 light years from the center out to the edge, right? And we're about 27,000 light years, okay? So what this is saying is basically take 27,000 light years, okay, make a circle, kind of like you saw me doing, and within that, within the sun's orbit, is about 1 times 10 to the 11th solar masses. Now remember what scientific notation is. It means that we would have to move that decimal over 11 places. So what that means is 1, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that many solar masses. It's within. Well, to kind of put it in perspective then, our entire Milky Way galaxy is one more zero beyond that. Okay, so the Milky Way galaxy is that massive. So if you do the subtraction then, and I'll kind of go back to this, if you take, okay, this is the whole Milky Way, this is the sun, this is our nuclear bulge, okay, so this is the sun's orbit, so if you take this, okay, it's accounted for. All of the other stuff, which is kind of the edges, which we know it gets thinner, the Milky Way galaxy gets thinner, okay, it's actually 9 times the mass that's inside our orbit. Okay, so there's definitely mass that's not seen, because what's beyond our orbit is just kind of those disk of stars. So that's kind of, and this is the picture I alluded to like 4 or 5 slides ago. So is this not adorable? Remember the video we watched, a speck on a speck on a speck? This actually is looking at, the blue thing is the Milky Way galaxy, edge on. Okay, and you can kind of see the cute little nuclear bulge. And then we talked about the halo region outside the Milky Way galaxy. Okay, those might be globular clusters of stars, that's fine. But then kind of that grayish area, it's kind of a gray and then it kind of peters into black. That actually is with our galaxy, and that is mass that's counted in our galaxy, mass that affects our galaxy. But there's nothing to be seen out there. Dark matter. And how do we know it's there? Well, it influences how matter behaves within our galaxy. One of the things it influences is the rotation of stars as they orbit our galactic nucleus. I like the term galactic nucleus. So this slide kind of talks about something we talked about before, not only what we know, but how we know what we know. So this idea of if you have a galaxy that is, it would have to be kind of edge on, okay, it might be a little bit face on, but you get this, what we call radial motion. As it moves towards you, you get a blue shift. It moves away from you, you get a red shift. Ooh, I said that wrong. I said that right. Towards you, a blue shift, yeah, away from your red shift. So actually, we can get to how stars are behaving in other galaxies with regard to their rotation. And so this actually is a curve, kind of like we made a minute ago with the stars in our Milky Way galaxy. Each color is a different galaxy. And I just am amazed that people take the time to do this. Isn't that awesome? So these, again, you kind of see basically instead of the orbital, or instead of the speed like kind of decaying like the outer planets do in our solar system, it just kind of stays up high like that. And the only thing that can explain that is basically there's dark matter that encompasses the galaxy. Like, oh. But one of the things that we're going to get to in this chapter is that dark matter actually was a player in the formation of galaxies. Dark matter had to be there, okay? Or galaxies wouldn't do their thing. And what makes up galaxies? Stars. So dark matter actually has to be there for stars to birth, okay? This kind of switches gears. Instead of, those were all spiral galaxies. These are elliptical galaxies, Okay, but we see still around elliptical galaxies dark matter. Okay. So speaking of elliptical galaxies, galaxies are organized in clusters, and I think I've mentioned that before. But is this not creepy or what? This is a cluster of galaxies. Okay. And elliptical galaxies are notorious for being crazy. Elliptical galaxy clusters are notorious for being just crazy big. So there actually are 3 ways that we can look at a cluster of galaxies like this. There are 3 ways, and we can get to what the mass is. And not so surprising, what we're going to see is basically kind of strewn between those galaxies is dark matter. Well, if each galaxy kind of has a halo of dark matter, then if you get a cluster of galaxies, there should be kind of dark matter kind of strewn between them. Okay, and that's what we see. The first way of measuring the mass of a galaxy cluster is Doppler. Okay, so basically you get a blue shift if it's going towards you, you get a red shift if it's going away from you. And so what you do kind of collectively is to kind of look at the dance of these galaxies as they interact. And if something's moving, there's a force making it move. Okay? So actually then they can get a sense, they can map the dark matter within a cluster of galaxies. And also get a collective mass of the galaxy cluster. And so what they've done using that method, for instance, a cluster like this, is you can see the baryonic material, okay, the light, from the light that the stars emit. See, stars are normal. Stars are atoms and molecules and stuff. I suppose molecules, stars. That's normal matter. But there's mass that is not normal, okay? Mass that we can't see. About 50 times the stuff you can see, okay, in these clusters of galaxies. The second method, and this was like an opening slide, again, this is a cluster of galaxies. These light little kind of pinpoints of lights are galaxies. And you can get a sense for what the mass is and where the mass is by taking its temperature. Okay, and that's, to me, an interesting sort of feat. Remember we talked about objects at different temperatures emit different fingerprints with regard to their radiation curve. Okay, that's kind of what we do. They do. The last one is actually my favorite. Oh, by the way, so in this example, again, if you talk about normal matter versus regular matter, okay, normal matter about 15%. Okay, that's because it's normal because we can see it. Okay, we can see it through the stars and know the mass of the stars. Dark matter, 85%. Okay, dang. But like I said, this is starting to say this is one of my favorites. Okay, this is actually getting to the mass of a cluster of galaxies by the dent it makes in the fabric of space and time. So going back to that chapter on what Einstein said, the concept of basically that space and time are kind of interwoven. And so actually, when an object that has a little bit of density to it sits on this fabric, it kind of makes a dent. Okay? And related to that, we talked about, do you remember there was a figure that had the sun setting here, and basically there was a star behind the sun, and because the sun was making a dent in space-time, the light from that star kind of went out and around and back. Okay, so honestly, and this was like an experiment, I think I showed you that this, back around the time of World War I, the scientists actually went and experienced a total solar eclipse so he could see the star. Okay, so basically the star is really behind the sun, but he could see it over here because it was bent around. Okay, and so it's called gravitational lensing, and that's the third way. So what happens is that whole set of galaxies, cluster of galaxies, actually makes a dent in the fabric of space and time. And so what this example is showing you is that there is a blue galaxy beyond that, okay? And so that the light from the blue galaxy comes out and around. So its last known trajectory actually looks like it's over there. Not only that, but it can actually go out and around on the other side. So you basically have twin galaxies. Okay, you're seeing them, okay, but the galaxy is really behind the cluster that's doing the lensing, gravitational lensing. No, is that not amazing or what? So you're like, I don't believe it. Well, here's a photo, okay? Those smears with the little arrows there, okay, that is a galaxy behind this cluster of galaxies. Okay? And so going back to how do we know the mass of a cluster of galaxies? Well, you know how much gravitational lensing it's affecting, okay, on light around it. And actually, just like our lenses can make us see better, and actually one type of telescope, refractor, uses lenses. Okay? Scientists can actually use gravitational lensing to take distant objects that they otherwise would not have been able to see, to bring the light together to see distant objects. So gravitational lensing can get us a fix on the matter of a cluster of galaxies. And again, then you can go ahead and do kind of the math, compare what the normal material, the baryonic material, versus what you know the cluster is from its gravitational lensing, and then you can know how much dark matter there is. Okay, so this is a pretty good little video. Last thing today. So I kind of said this before, this idea that I think scientists think that sometimes there's something we call dark matter that is just normal matter. It's just not lit up. So for instance, we talked about sometimes when stars are born, they don't have quite enough mass to go ahead and create nuclear fusion in their core. They are what we call brown dwarfs. So those will just kind of cool down and be something, okay? And so those could be actually some of these things that we call machos. So macho stands for massive, compact halo objects. So compact because, well, they're probably all kind of squished down. Brown dwarf would be pretty dense. And halo objects because most of the dark matter around a galaxy is found in the halo region. But the LHC, the Large Hadron Collider that we saw a minute ago, actually the Higgs boson would be actually along this idea of a WIMP. WIMP stands for, yeah, the macho and WIMP. WIMP stands for weakly interacting but massive particles. Okay, so and even though this says the best, I really think that I guess one more slide. I really think astronomers think there's probably a combination of the two. This slide is just showing you maybe the machos, the ordinary baryonic material. It's showing you a gravitational lensing of an object that we could not see, but we can see the lensing effect in this middle slide of the light behind it. Okay, so we know that there's machos out there, but like this says, there's not enough of that ordinary matter, that's not lit up to account for all the mass that we see. So we really do have to have WIMPs involved. Okay, so that's a good place to end. All right, have a good weekend. We'll see you on Monday.